Hello everyone, we are Team Russians and our problem statement is real-time groundwater resource evaluation with DWLR data. Water radar aims to make groundwater management proactive, trustworthy, and inclusive. We start with real-time data collection from DWLR APIs with the support of mobile view that you can communicate across several stations from your phone. Once the data has been collected, it is broken down into daily and seasonal formats for useful information analysis that will include recharge index, water table slope, rainfall correlation, and seasonal trends. When groundwater level breach significant water level thresholds, the system notifies you immediately, alerting you to mitigate actions. In more severe events, a crisis activated AI chatbot is made available to the authorities with regional data set to assist in urgent response strategy development. And there is a visual dashboard showing charts of water availability, water level, recharge regime, and risk status. We also show a 3D AR representation of acquired aquifers. In the spirit of ensuring access to everyone impacted, all alerts to user are made available in 20 plus Indian languages through Bhashini. Data and reports can be extracted in downloadable form in CSV and PDF formats for record keeping and further analysis. And included will be a decision support framework that provides a role-based response guide informing alerts to users, researchers, and field officers the most relevant information needed to react. Now, further will be explained by my team.
Technical approach. First, recharge estimation. Real-time data of groundwater level from DWLR sensor is ingested with weather data in our data layer. From here, data is taken to anomaly detection, in which our model is trained on previous 10 years of data to sense any kind of fault, checks for spikes, drifts and gaps in the data, then cleans it, validates it and pass it on to groundwater forecasting layer. Now, in feature engineering layer, it takes all the features like rainfall, temperature, evaporation, transpiration, land use, soil, irrigation demand, and creates new features from it. Now, these features are taken into groundwater forecasting layer, where our models such as LSTM and XGBoost works on it and predicts groundwater recharge percentage and horizons, meaning the trends of 7 days, 1 month, and 6 months, where the expected outcomes are groundwater level water trends, which is given by LSTM model, recharge patterns, then forecasting and groundwater level based on past data. This is done with XGBoost, recharge estimation time, and horizons, meaning the trends. Now, here our logic section generates critical alert where certain threshold when hit provides with certain alerts and reports. All the data from the data layer and outputs and alerts are taken into decision support model. Now we will look into our code. This is coding process in which these are the libraries necessary for the model to use. Then we import data and then anomaly detection model is run on them. We visualize any kind of anomalies like this graph, which indicates there are two anomalies in the data. The data is taken to feature engineering where new features are created on previous and standard parameters. Forecast for preparing, we scale the data so that model can read and actually perform calculations on it. Then we will visualize the trend. This trend is predicted via LSTM. The groundwater recharge process have a trend from May to August. It actually recharges very quickly, but does not at the end like January, February, and December. Now we will find out the trend lines. These are the trend lines from the date 2022 to 2024. After that, we will use the multi-model forecasting versus actual. This is done with LSTM and random forest XGBoost to explain this predictions.
I'll walk you through our decision support chatbot, which works seamlessly with the groundwater forecasting workflow. This process is straightforward and based on a powerful RAG architecture. First, for data collection, we feed all the official reports and research papers related to the groundwater in our system. Then, during data splitting, all the information is broken down into smaller and logical chunks. These chunks are then converted into embeddings. These embeddings are then stored into the vector databases. Now, when a user submits a query, it is converted into the same vectors and then we perform a data retrieval step searching the database for the relevant chunks of information. Finally, these retrieved chunks and the original questions are sent to the prompt construction layer, where all the data is sent to the AI model for response generation, providing a concise and data driven answer. Crucially, our system also integrates with critical alerts. When an alert is generated, our RAG pipeline automatically retrieves relevant context and generates a summary explaining the alert's cause. Now, I'll show you the code. This is our entire code. Here we have the data folder where we can insert our data which is related to the groundwater. Now I'll be showing you the working of the chatbot. This is how our chatbot looks like. Now, when we ask a query like explain groundwater recharge methods, then it will give a concise answer that how can we recharge the groundwater. For example, if anybody asks a decision question like our area had a very little rainfall this monsoon, should irrigation be restricted? Our chatbot searches for the relevant documents and give a concise answer. Our plan is to integrate this decision support chatbot directly into our main groundwater monitoring app. This will make our system more user friendly and accessible to researchers, farmers, and policymakers.
Now moving forward towards the key features of UI. The dashboard represented current water level, groundwater level status and recharge. Moving downwards, the groundwater level has been plotted on daily basis in graphical representation. The recharge estimation has been plotted the range of 3 months, 6 months, 1 year and 5 year. Now moving forward towards the map, the DWLR station has been plotted and pinpointed on the map. On clicking the DWLR station, the short summarized detail appear. On clicking see more detail, all the detail about the DWLR appear, which has location, water level, environment, time series analysis, telemetric status, aquifer, and all many more details. User can download the complete station reports, groundwater report, aquifer information, all in various file format like JSON, Excel, CSV. Thank you for watching.